start. So from here, we're going to head into chapter 2. So as I started saying a bit early, I believe in you, laptop, you can do it. Can you not do it? It'll get there. That laptop struggles. All right, we can get this here. So chapter 2, there it goes, is where we kind of shrink everything down, right? We started super broad. What is life? What is science? What is biology? And now we're going to go into that kind of hierarchical structure we were talking about, right? Cellular and organismal, to the smallest first little step. We're going to start at the atom in chapter 2, molecules. Chapter 3, we're going to build into macromolecules. Unit 2, we're going to start making organelles and then cells, right? And so the whole class from here is basically going to work through that framework that we kind of talked about on Friday, starting with a little chapter 2 sidebar into chemistry. Superficial chemistry, nothing super, super intense. We just need some vocabulary, basically, is what we're doing here. Okay, so we're going to talk about molecules and water and stuff that's important to living things. Okay, so first section, we're going to talk about elements. What are atoms? What are elements? Right? How do we describe them and name them? Right? And then we're going to talk about how the structure of those atoms, right, affects the way they function for our purposes in living stuff, right? So we're pulling that structure and function theme, right, from the unifying themes of biology. That was one of our unifying things. We're going to talk about where electrons are in an atom, because there's things going on in the nucleus of an atom that's important. But for living stuff, most of the interactions of atoms and molecules and things are happening at the electrons. So that's where we're going to kind of focus in on towards the end here. So an atom, basic little atom here, very generic little picture. So all matter is composed of atoms, living or not, right? The table, me, the tree, the glass, the air, right? Everything is atoms. They're composed of 3 kinds of particles, right? That they're kind of, without getting into quarks and other weird tiny, tiny things, protons, neutrons, and electrons, right? So protons and neutrons are found in the nucleus, right? In the center, kind of all packed together. Protons are positively charged. Neutrons have no charge. They are not positive or negative, they're neutral, right? And then kind of floating out in the space around the nucleus, you have the electrons, right? Which carry a negative charge.
Yeah, it's just like a little bird diaper for parrots, but just put it on duck.
Oh, that's fine. We should get one.
You're not muted. Right. So our example here is lithium, right? So we've got our nucleus with 2 protons and 2 neutrons, and then 2 electrons floating on around the outside. It's one of the smaller atoms, obviously. And so we describe atoms, we'll get to this a bit more, by their atomic number, which is equal to the number of protons. So in this case, the atomic number for lithium is 2. 2 little protons right there in the center. So we've got atoms, and we group atoms into elements, right? An element is any substance that can't be broken down into another substance, right? The lithium atom or this beryllium atom is made up of particles, but it can't be broken up into any other thing. Once you break it apart, it's just the particles, right? So it's kind of the basic units of matter, right? So an element is any substance that can't be broken down into any other substance, right? And we define them by their atomic number, by the number of protons, okay? So atomic number is equal to the number of protons, right? And it's a nice way to group them because atoms with the same numbers of protons behave similarly. It's just a useful way to categorize them. And so these are what we kind of name as elements, atoms with the same number of protons, right? And because of the number of protons, which are positively charged, they will have a certain number of electrons, and those electrons then determine the behavior of the atom. Okay. So atomic number of beryllium, it's a little fuzzy. Can you tell what the atomic number of this atom is? If you squint a little bit. Yeah, it's 4. Yeah, 1, 2, 3, 4. Also generally equal, if the atom's not charged, we'll get there in just a second, right? Your number of protons, which are positively charged, should match the number of negatively charged atoms in a nice kind of balanced situation. Yeah, so the atomic number is 4 for beryllium. Not that you need to memorize the atomic number of 4, it's just easier to draw the small ones. All right, atomic mass. All right, so sidebar at atomic mass. Let's define mass versus weight, because sometimes if we're just talking, we tend to kind of bop the two back and forth. But this is another one where kind of in our science classes, we've got specific definitions we're worried about. So mass is the amount of a substance, just the literal amount of a substance that is there. Weight is the measure of gravity on that substance, right? So mass is always the same, no matter where you are in the universe, here, the moon, Jupiter, the mass is the same. The amount of stuff is the same. The weight changes, right? Because weight is relative to gravity. I weigh more here than I would weigh on the moon. Yeah. Since we all kind of exist on Earth and all of our stuff is on Earth, we tend to kind of throw these back and forth because we're all existing in the same amount of gravity. But we're talking specifically about mass, the amount of stuff that's there, right? So atomic mass, the amount of stuff in an atom, is the number of protons and neutrons in the nucleus. We don't count the electrons. They are so tiny relative to the protons and neutrons that they're negligible, right? Protons and neutrons are significantly larger than electrons. So for example, in beryllium, we've got 4 protons, 4 neutrons. So the mass then is going to be 8, right? So beryllium, atomic number 4 for 4 protons. It's also got 4 neutrons. Those are all of the big particles in there. So the mass is 8.
So are you those red, the red ones are the protons and those things that's in the middle, are those the neutrons?
Yeah, so the red ones are the electrons around the outside. So there's like light ones and dark ones, kind of blue and white ones in the center. Those are the protons and the neutrons, right? So the darker ones are, not that protons are darker, just the way I drew them. The protons are the dark ones, and there are 4 of them. The lighter ones in the center are neutrons, also 4 of them. So you add those together and you get an atomic mass of 8. There are 4 electrons also floating around. Those are the red guys, but they are super, super tiny. In reality, I can't draw microscopic things on a PowerPoint in a very accurate way. But we don't count those in the mass because they are so small relative to the rest of the atom. All right. But those electrons are important, so we got to take a bit of time and talk about what they are doing. So the electrons are located in orbitals, right? It's just kind of how they're organized around the nucleus. We're not going to be as worried about orbitals, but just to know that the electrons they're not in the nucleus, right? They're kind of out in these other spaces, far away from the nucleus, kind of floating around. But they balance the charge of the protons, right? Protons are positive, electrons are negative. So if you have equal numbers of protons and electrons, then the charge is balanced. You have equal positive and negative charge. So the atom is neutral, right? So a neutral atom has the same number of protons in the nucleus as it has electrons kind of floating around in those orbitals outside the nucleus. Right? But occasionally and frequently in biological systems, we see things called ions. And in ions, the number of protons does not equal the number of electrons. All right, they come in two flavors, cations and anions. So a cation is an ion, is a charged atom in which you have more protons than electrons, more positives than negatives. Right? So that atom is positively charged. It's got more protons in the nucleus than electrons floating around it. Right? Frequently something that happens to sodium, it loses an electron and becomes a positively charged sodium atom. Right? Which we usually write this way, right? Sodium is Na on the periodic table, Na plus, it's got a charge of +1. Conversely, you can have an anion. An anion is an ion or a charged atom where you have fewer protons than electrons. Right? So you have fewer positively charged particles than negative ones. So the atom has a negative charge. Right? You got more negatives than positives. You see this sometimes with chlorine. Chlorine will gain an electron, right? We'll get an extra negative charge, so it becomes a negatively charged atom. Right? When we start talking about molecules and like biological macromolecules towards the end of Unit 1, we'll see these charges doing stuff, right? So cations and anions. Cations are positively charged, anions are negatively charged. All right. So we can have different numbers of electrons. We can also, looking back to the nucleus, and just side note, there's a lot of kind of numbers and specific details on this slide. You don't have to memorize the half-life of carbon. I know I'm kind of reaching ahead a bit. For me, we've got some terms to define, but don't get too bogged down in the examples themselves, unless you just want to, right? So we can have differing numbers of electrons. That gives us ions, charged atoms. There are also cases where we will see different numbers of neutrons in an atom. Right? With our initial examples, right, we had equal numbers of protons, neutrons, and electrons, these kind of happy little uncharged stable atoms. If for some reason you have a different number of neutrons, you call that an isotope. Right, so carbon, which has 6 protons, right? Most of the time, 99% of the time, 99% of carbon has 6 neutrons. So 99% of carbon is 6 protons, 6 neutrons, atomic weight of 12, atomic mass of 12. But there are 3 isotopes of carbon that we find in living stuff. All right. Most of the time, you've got 6 neutrons, 6 protons. Most of that last little 1% of carbon in living stuff is carbon 13. 6 protons, 7 neutrons. The rarest one, the one that is found kind of in the least amount, is carbon 14, which would be 6 protons, 8 neutrons. And that's unstable. Right? A carbon 14 atom, right? You could kind of imagine in your head, it's a little bit out of balance, right? So it's got 8 neutrons to its 6 protons. And so we call that, because it's unstable, the word for that is radioactive. So when somebody calls something radioactive, this is what we're talking about. The atom itself is unstable. So it's a radioactive isotope. It's an isotope because it's got an unusual number of neutrons. And because it's not stable, we call it radioactive. And so because it's not stable, it will break into smaller elements over time in a predictable way. So this breaking down of carbon 14 over time is called radioactive decay. Carbon 14 will decay into other elements over time, right? And so, like I said, the decay rate is constant. And this is where that idea of half-life, carbon dating, This is what carbon dating is using to figure out like how old fossils are, right? If I know, so we find a fossil, some fossilized piece of a tree, right? And there's carbon, right? You can like use mass spectrometer, whatever. There's carbon in the tree. And I know that initially what percent of that carbon was carbon-14, okay? And then I look at how much carbon-14 is in my fossil proportionally. I can figure out how old the fossil is because you don't need to memorize this number, but every 5,730 years, there will be half as much carbon-14, right? Yeah, I'm not gonna make you do this math. This is just how carbon dating works. And there are other radioactive isotopes that you can use for dating this way. All right, so main takeaways, isotopes are atoms with differing numbers of neutrons. When they're unstable, we call them radioactive. They decay over time. We can use them to measure the age of things. All right, isotopes. Now, back out to the electrons. Isotopes matter. Electrons are still more pertinent for our purposes, okay? So, like I said, we've got electrons, 2 electrons per orbital, right? Spaced out around an atom, around the nucleus. They can be in different shapes, right? They can be spherical, they can be dumbbell shaped. We're not, that's for your chemistry class, other than to know they're existing in these orbitals. They hold at most 2 electrons. And because of this, because you've got 2 electrons per orbital in these spaces around the atom, atoms are mostly empty space, right? I've drawn this nucleus, like I've drawn the relative sizes here kind of small, not small, close together, because otherwise, right, if I had this nucleus this size here, the electrons would have to be like accurate to an atom, like outside the room, right? The protons and neutrons are all close together in the nucleus, and the electrons are just kind of way out in space, right, around the nucleus. So when 2 atoms interact, the nuclei aren't interacting, right? Those clouds of electrons around the outside are what are interacting, right? If you start knocking nuclei together, that's nuclear fusion, and that's how you like blow up continents and things. That's a different situation. Most of the time, only these kind of outer electrons are interacting naturally. All right, so we're concerned with the electrons. Now, these electrons floating around the nucleus contain energy, which is important for us, right? Because we can use that energy. And so we say they exist at different energy levels, depending on how far from the nucleus they are. This is not the same as orbitals, right? Dumbbell orbital kind of shows this, right? So an electron existing, we're talking about literally how far they are from the nucleus. Depending on how far they are from the nucleus determines how much energy they have, and we're usually looking at the electrons that are existing kind of on the very outside of an atom. All right. All right, energy levels. So on the outside of these atoms, right, these outermost electrons, whichever electrons are existing furthest from the nucleus, can move around, can interact, right? And so these outer electrons can sometimes be transferred between atoms. And this happens frequently in biological, physiological systems, right? So we can have one atom lose an electron, and then another atom gain that electron. When an atom loses an electron, that's oxidation. It is oxidized when it loses an electron. Okay. Pretty much always, if one atom is oxidized, if it lets go of an electron, a nearby atom will be reduced. It will gain that electron. Right. So when an atom loses an electron, it is oxidized. When an atom gains an electron, it is reduced. Okay. Generally speaking, these reactions, oxidation and reduction, are coupled. They tend to happen together. Something is oxidized, something is reduced, right? And so we tend to kind of refer to them collectively. We just lump them together because if one's happening, usually the other's happening, and we just call them redox reactions, right? Something's oxidized, something's reduced. And that whole process is a redox reaction. Reduction, oxidation, reaction. How are we feeling? Making it? Chapter 2's. It is what it is. All right, redox reactions. Now, that's section 1. Section 2, right, we've covered like really broad strokes chemistry, right? We're gonna kind of narrow it down to the stuff we find in living systems, right? Because that's just what we're more interested in for the purpose of this course. So we're going to talk about kind of how the periodic table is organized, right? Given atomic structure and things like that. And then we'll narrow that down basically to the elements that we're going to be seeing and dealing with in class, right? So the periodic table is displayed according to atomic number, which is the number of
atoms.
I think I heard it a little louder, maybe.
Atoms.
So not the number of atoms. So within an atom, its atomic number is the number of
2
protons. Yeah, the number of protons, right? So we start with 1 and we just keep counting, right? All the way up through 90 natural elements, however many there are, right? So they're organized 1 to 90, roughly, right? And they're put into columns, right? So we go 1, 2, 3, 4, 5, 25, 26, 27, 28, all the way to 90 down bottom right. The columns refer to the valence electrons, the number of electrons at the very outside, at the outermost energy level, right? Which is handy because those outermost electrons are the ones that are going to interact with other atoms. It's going to help determine the behavior of the atom, right? And in things that we find in living systems, they generally have 8 or fewer valence electrons. Okay. All right. So in living systems, right, we've got about 90 elements, that's fine. For our purposes, we're going to be looking at about 12. Carbon, hydrogen, oxygen, nitrogen, sulfur, sodium, potassium, calcium, magnesium, iron, and chlorine. You don't need to memorize the whole long list. Don't worry about that. Mostly, I mean, if you wanted to memorize a set, these 4 right here make up 96.3% of your body weight. Carbon, hydrogen, oxygen, nitrogen are the biggies. We'll talk about them the most. We'll see them over and over and over again. Such that compounds with carbon and hydrogen specifically are organic compounds, right? They are found in all the basic building blocks, macromolecules that make us, carbon and hydrogen, and then usually oxygen. All right, so these are very common. Don't worry about memorizing them. Be familiar with these 4, but you're going to see them so much. I don't know that you'll have much choice other than to kind of have them stuck in there. You'll see these in lab. You'll do kind of organic molecule modeling and stuff if you're in the 1101 lab. All right, so we've got these common elements from living systems. All right, we have talked about atoms, categorized them as elements, talked about the ones that we're going to be most concerned about in here. So That was the atomic level in that cellular organization. The next level was, where do we go from atoms? After atoms, in like that organizational hierarchy, atoms come together and make molecules, right? Section 2.3, we're going to start making molecules, talk about how molecules are made. So which elements are likely to form ions, which are going to be kind of important physiologically. We're going to talk about covalent bonds and then kind of polar versus non-polar covalent bonds. These are kind of the most common things we're going to see happening in biological molecules. So molecule, definition of a molecule is just a group of atoms held together by energy, right? Because all of those electrons around the outside are holding energy, right? Potential energy. So groups of atoms held together by energy in a stable association. So atoms that have come together and are staying together. So we're going to walk through kind of each of these bond types of chemical bonds, but we've got three main ones that we're concerned with in here, right? So we've got ionic bonds, and that's the bonding of ions, right? So we've got atoms that are positively and negatively charged. So that interaction is an ionic bond, right? Or one atom is losing an electron to another atom, right? Again, we'll come back through these kind of with examples after we walk through them kind of briefly. Covalent bonds are where you've got atoms that are sharing one or more pairs of their valence electrons. Okay, so we've got ionic bonds, covalent bonds, and then hydrogen bonds. These are the weakest ones that we're going to talk about. And this is where we've got kind of a really weak bonding that's just happening between hydrogen atoms. We'll pick that apart. That's going to become really important in water when we talk about the way water behaves. Those hydrogen bonds are important. All right. So molecules are groups of atoms, any group of atoms. Compounds is basically just a more specific subset of molecules, just to kind of make the differentiation. A compound is a molecule with more than one element. Right, so oxygen, like atmospheric oxygen, we usually write as O2. It's two oxygen atoms stuck together. So that's a molecule. A compound would be something like water, like H2O. So we've got two different kinds of atoms stuck together. All right. All right, so let's talk about bonds. Ionic bonds was that first one. Ionic bonds tend to form crystals. Okay, so we've got this positively charged sodium with this little extra electron. Remember we talked about that happening before. Right, we've got chlorine with its little unpaired electron. And so what you will find when we start looking at these bonds happening is atoms want their electrons to be paired. And they will behave such that their electrons get paired. Right, so sodium in an ionic bond is going to give away its electron to a chlorine, right? So now sodium, because it's given away its electron, has no unpaired outer electrons, but it's given one away, so it's got a positive charge. Chlorine has taken sodium's electron, so now it has an extra electron, it's got a negative charge. So they remain associated. They form these crystals, right? So when ionic bonds happen, this is table salt, by the way. This is why table salt makes all these little squares. These atoms come together, they trade these electrons so that they become more stable, and then they form this kind of crystal structure, right? So ionic bonds, right? Now, interesting fact, living systems always contain water. We're going to spend some time talking about water. Water dissolves ionic bonds, right? You know this, if you put salt in water, the water dissolves the salt dissolves, right? And so ions become important physiologically, right? Because we're full of water. So the ions in our body don't form crystals, right? That would be a bad time if all the sodium and chlorine in your body just started forming like little rocks everywhere. Right, you're full of water, so salt never forms crystals, or shouldn't be forming crystals inside of your body. right? So our body uses these charged particles to do stuff. So we'll be coming back around to that. Covalent bonds are when two atoms share valence electrons. So for example, hydrogen has one little lonely valence electron. That's unstable, it doesn't like it. But it's not carrying a charge, right? Because it also only has one proton. We've got one proton, one electron. We don't have a charge, but we're still unhappy because we've just got this one lonely electron. So they'll share. That's nice. So hydrogen, hydrogen gas, H2, has no net charge, but now is sharing these electrons. So it has a full outer energy level, right? We're talking about energy levels, these outside electrons, and no unpaired electrons, nice and stable. Nice double covalent bond. We're sharing, or single covalent bond rather. This one pair of electrons. Nitrogen has 5 valence electrons, 5 protons, no charge, right? But we've got 3 sad unpaired electrons on either side. So if 2 nitrogen come together, they want their electrons paired, they'll pair all of them up. So nitrogen gas forms a triple covalent bond. That's a super, super, super strong bond, right? They're sharing 3 pairs of electrons between them. They're like bound together. There's still no net charge. We didn't gain or lose any electrons, right? But our outer energy level is full. We have no unpaired electrons, right? Covalent bonds share electrons, right? All right, so we're gonna do this on Wednesday because we've only got like a minute left. All right, so we're gonna leave off there. We're gonna pick up and finish covalent bonds on Wednesday. Remember, if you haven't done your quiz and lecture journal, do those today. Remember, question 3 is funky. I'll fix that myself. Don't stress. When you know you answered it right and it still takes off stuff, I'll fix it. Okay, yeah.